And this is the second video of us going through the free response for APC Mechanics in the year 2026. This was released, I think, earlier today. This one hopefully will go much faster, although this is the exam that just keeps on giving. I've heard that the other versions are also very challenging. I once again really like this question. We're going to go through, and this has a little bit of everything. This is our translation between representations question. This one is worth 12 points, as they always are. For this type of question, and has a little bit of everything. The recommended time is usually about 25, sometimes 30 minutes. It fluctuates depending on what all they're asking you to do. Now, our last video went much longer. Hopefully this one will go a little bit more in keeping with the time that you would have available for the actual question. We're going to jump in. I've sketched out not only the solutions on this, which were a doozy, but also what I think is a good representation of where the points would be. As all TBRs do, at the beginning, they have you create something that's usually free body diagrams, bar charts, or other diagrams. In part B, before I get ahead of myself, part A is pretty much always worth 3 points. Part B is going to be a semi-challenging derive. This one is a little bit messy with what you have to do, but it's not actually overly challenging. There are just a few things that you kind of have to catch in order to be able to move forward. And so that's what makes that one a little bit more challenging. C is usually graphing something, almost always velocity as a function of time or acceleration as a function of time, but velocity as a function of time is very popular. This is worth 3 and is almost always. And then part D is they ask you to compare some stuff from a previous part. They kind of change things up and predict how that would change things from a previous part. Okay, jumping in. We've got, this is actually very similar to the question I had for Unit 4. Momentum, when I went through the introductory class as a physics major many years ago. Big difference is they were a little bit nicer to you all because when I had the firework that went up into the air and exploded, it exploded into 3 pieces and we had to conserve momentum in both the X and Y directions independently. That being said, okay, we're launching a thing up into the air. It starts at x equals 0. It's launched up with an initial velocity of magnitude v0 at an angle theta. That's basically what this is saying. It has a mass of 4m. I would read the full thing, but let's try and keep moving on this. Flies up into the air. It is also moving forward when it reaches the apex. So at time t1, immediately, let's see. They do say that the projectile is launched with initial, when the projectile is at its highest point in its trajectory, so its apex, it breaks into pieces Q and R of masses m and 3m respectively. It's basically a firecracker, gets up to the top, and then as it's going like this, right when it reaches the top, it explodes. One piece goes off this way, one piece goes off that way. And then eventually, they come back to the ground and crash at the following locations. The small piece that goes backwards ends up back where we launched from, and then the other piece goes forward to an unknown spot that we are calling x2. Note, figure not drawn to scale. Okay. First thing, part A, horizontal and vertical components of a momentum vector are represented. This is the first time that I recall seeing something represented like this on the AP exam, especially with the new one. I'm getting flashbacks to something that they told us at a summer institute a few years back, but this seems a lot more manageable. Key things on this are we are representing a vector quantity, but we are doing it with kind of a scalar approach with the bar charts. This is a lot like energy, so you might think of this in terms of like energy, but your big thing is you've got momentum in the x direction and momentum in the y direction. What does that mean? So if you have our initial velocity vector points up like this, v0 at some angle theta, we're going to have an x component like this, v0 cosine theta. We're going to need this diagram anyway, so this isn't just me rambling, v0 sine theta. So we're going to take our initial one and we're going to split it up like that. What they're representing is this, that at launch, they're calling this 4 units. And at launch, they're calling this one 2 units. But here's the thing. They're giving you this information at launch, which is here. And then it flies up into the air, and we're being asked about up here when it is at its apex. Now at the apex, our velocity in the y is actually going to be 0. It stops going up and starts going back down, so our velocity for the firecracker in the y is going to be 0, but our velocity in the x is still going to be v0 cosine theta, which they define to be 4 units. I want to emphasize that because one of the things that they're looking for on this is you keeping track of the actual numbers. We have 1, 2, 3, 4 units. We have 2 here. Okay. Now, what they've got is draw shaded bars to represent Px and Py for pieces Q, the one that goes backwards, and R, the one that goes forwards. Let me double check that I've got that right. Yes. And represent those. Let's see. Represent the magnitudes of the components with the momentum by using the heights of the shaded bars. Represent any momentum component that is equal to 0 by drawing a distinct line on the 0 momentum line. Okay. There are a few things that we kind of have to surmise on this. First thing that's going to be the easier of the two is our y components. Well, we have 0 momentum in the y direction for either of the pieces because our total system has none. So in this, I don't know if I can actually write on here. I'm going to give it a try. Yeah, I can. They say put a distinct line. For the APC exam, the instructions here represent any momentum component that is equal to 0 by drawing a distinct line on the 0 momentum line. I don't think that you would run into problems if you also wrote 0 above this. The only reason that I bring this up is I teach all the other AP classes as well. They had something like this on some of the prep materials for AP2, where when you had a bar chart and you had a 0 value, draw the distinct line, but don't be afraid to write 0 along with it. I am very convinced that the graders would be perfectly fine with that, and it just reinforces, hey, you're sending a clear message to us that that would be 0. I'll update this if I find out that that's not allowed, but I really think that that might be a good move. So if you're using this to study for the future, if something's 0, don't be afraid to write, hey, this thing is 0. Follow the instructions. They might not give you credit if you just say 0, but it doesn't hurt to reinforce that. Okay, here's the other thing. What I would be looking for is this. We know that piece Q goes backwards. On top of that, here is where some of the stuff to get the full correct answers in the time that you're needed, you need a little bit of practice on this and seeing the symmetry so that you can actually come to some conclusions. This thing flies up this way in a certain amount of time, and then the time that it would take to go up to the apex, and we're going to use this later, is the same as it would take to go back down. So in other words, 0, T1, and T2, T1 pretty much has to be half of T2. It goes up, and since it's on flat level ground, the time it would take for it to come back down would be the same. Our explosion does not have any component in the y direction, so our center of mass would go up and come down. So this is right in the dead center. In short, that's one of the key things that I think you need in order to get full credit on this, if my supposition is correct. Because piece Q ends up back where it started, it has to have the same velocity going forward or going backwards as it did forward. So another way of writing this would be whatever the initial velocity was for the thing, v naught cosine theta, after the explosion, it needs negative v naught cosine theta. In other words, it needs to be going back the opposite direction. Well, in this case, we have a total system of, we have 1m times v naught cosine theta from piece R plus 3m v naught cosine theta. This is getting us set up for the next part, and I don't know if you'd have to have this absolutely perfect because you wouldn't know these values until you get to the next part, but there is some reasonability that you could actually do with this. Equals, let's see, this one then needs to be, this gives me a total of 4m v naught cosine theta. In short, I've got 1 times the velocity for R and 3 times that same velocity for Q. So I end up with functionally 4 units representing my total momentum. That ties back into me saying that there were 4 units total. Well, this thing needs the exact same velocity, same speed, but opposite direction. So this needs to be -1 v naught cosine theta to end up back where it started. So this needs to be my afterwards, my P final. This thing has to get back to where it started, so it has to go -1, and based on the total 4 units, that leads me to the conclusion that what you need is, for this one, 1 square here. It goes down 1. Okay, here's where the next part comes in. In fact, I'm going to start introducing the grading rubric on this because we started with a total of +4. I need my end to have a total of +4. I have -1 here, so I go 1, 2, 3, 4, 5. This is the correct answer. Both of these are 0. 0. This should be the correct answer. We're also going to demonstrate that this is the correct answer, where this ends up being 5 mv naught, and with it having a mass of 3m, we will find that it has a final speed after the explosion of 5/3 v naught. We don't know that yet, unless you've worked ahead, but this is a way that you could still come to the correct answer and not have to have derived fully the next parts on this. We do know that we need a negative value for this one, and since it goes back to where it started, it really needs to be 1/4 of the original value there, because that's how much momentum it would have. If you're not fully keeping with that, we basically have, it may be that you get 1 point, I'm convinced, for having zeros for both of these. Not just one, both of them. The next point is for having a negative value for this one because it's going backwards, and with this being APC exam, I expect that they probably want it to be -1 specifically to get that point. And then over here for this one, it would be, you get the point for having a positive value of this that when combined with your answer here would be equal to 4 units total. So if you get this one wrong and you drew it as -2 or something like that, this would need to go up to +6. I don't think that they're actually looking for the correct value on this because you don't know what that is. You can only come to the conclusion by conserving your momentum here. Okay, I'm going to erase this and we're going to move forward. Again, me explaining slows this down compared to what I would be doing if this were an actual test. Okay, but I think that those are the 3 points. 1 point, zeros. 1 point, -1, and 1 point for this one being a positive value that balances out with this one to be a total of 4. Okay, part B. This one's going to be a bit of a doozy. So everything that I've drawn here is actually applicable. For those of you who have gone through my class, we've got a few things that we need to take a look at. We are launching from here with basically we have motion where the thing goes up like this, it explodes, exploding time up here, and then we have motion where this part goes down here and this other part goes back here. Here's what I'm going to do. I'm going to break this up into sections. I'm going to call this one motion A. I'm going to call this one motion B. The reason that I have to split them up is I have different values for the velocities of the objects because of the explosion that happens very quickly up here. The explosion happens in a very short amount of time, I'm pretty certain it says. We are also at some vertical height h. You can use that, but as we mentioned before, the time for this motion is t1, and the time for this motion is t2 minus t1, but because of symmetry, this is also equal to t1. At this point, what I'm going to say is the time from here to here, I'm just going to call it t, and the time from here to here, I'm also going to call it t. There are 3 things that we're going to have to keep track of, but that's after we get our initial things set up. Now remember, this is a derive expression, so we need to, let's see what it tells us to do specifically. Derive an expression for x2 in terms of v naught, theta, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference sheet. So there are a couple different things that you could do on this. This represents a distance of, we're told that this is x1, and that this is x2, and that this, way back over here, is 0. Okay, these are not, the symmetry is for time, it is not for the actual distances involved. The reason why is it takes the same amount of time to go up and down, but it takes, since they have different velocities, this is no longer symmetric. So if you have done a bunch of projectile motion, if you haven't dealt with it exploding partway through, you might erroneously think that x2 is twice x1, but it is not, as we will see in our derivation. Okay, what I would actually set up on this is I need to know a couple of different things. For my students, we would organize this as follows. For motion A, I'm looking predominantly in the x direction because that's where I'm trying to find x2. My displacement is equal to x1. x1 minus 0, basically, but that's just x1. My final velocity is positive v naught cosine theta. My initial velocity is v naught cosine theta. My acceleration is 0, and my time I'm just calling t, because the time here was equal to the time here by symmetry. I don't think that you'll have to prove that. I think you can also just accept that, but that's one of the things that makes this extra challenging. Delta x for motion B is x2 minus x1. My initial velocity on this is, okay, here's where we're going to have to start what I would consider to be my actual derivation. But if I'm working through this, I would kind of organize my information like this. My acceleration would still be 0, and my time of motion is t. But I need to know how fast this piece, the big heavy one, is going after the collision. And for me, that's where I began my derivation, because I knew in the explosion that I would have to apply conservation of momentum. So here, I'm going to start by writing a fundamental principle of physics, which is conservation of momentum. My initial momentum of my system is going to be equal to my final momentum, both before and immediately after the explosion. I have the following: 4m v0 cosine theta. For the reasons that we described before. Again, some of this I had already laid out. We're going to keep moving. That is going to be equal to, well, I said that the other one was going negative 1m v cosine v0 cosine theta. And then that would be plus 3m times v, I'm going to call this r. Is this r? I think this one is r. I'm going to take just a moment and make certain that I'm calling it the correct thing. Yeah, R is the big one, just so I can keep track of my stuff here. Okay, moving forward. M v0 cosine, I can add this over to the other side. This is positive 4, this is negative 1. I add that over, and we end up with 5m v0 cosine theta is therefore equal to 3m vr. I divide both sides by 3m. The m's cancel out, and I end up with 5/3 v0 cosine theta. As a quick side note, 5/3 v0 cosine theta, that's my velocity in the x direction, and if I multiply that by 3m, I get 5 v0 cosine theta. Here is where on, oops, no, it was on the bar charts, but when I drew them out, -1 here and positive 5 here, that's where the 5 comes from. We just derived that 5. Okay, here's the important thing. This is how fast VR is going after the explosion, which is information that I needed. VR is, 5/3 v0 cosine theta. And that is the same for both of these, because in the x direction we have no net force after the explosion and before the explosion, which is where sections A and B are. The explosion happens very quickly. Okay, here is where my derivation would probably begin, because I know that I need that speed for piece R. Why am I looking at piece R? That's the one that goes to x2, the thing that I'm after. Eye on the prize. Okay, on this, now you have to get a little bit creative. For my students, it's been a long time at this point since we saw it, but we introduced complex kinematics way back in Unit 1, and I gave you an example problem where we were looking at an elevator that started up, accelerating, and then went at a constant speed and then slowed down, and we had to break motion into different parts like we're seeing here, because values would change in between those. So it's the same idea, just in a different way. This gets a little bit tricky, but one of the big things that I would say is the following. I know that I want x2. I know that I'm going to need to include time, because with 0 acceleration, we have a tendency of dividing by 0 and getting undefined answers. So broadly, we are going to use the kinematic equation delta x equals v0 times time plus 1/2 at squared for both of these. For A, that gives me x1 is equal to v0 cosine theta times t. And for my motion in B, that gives me x2 minus x1, that's my displacement, equals my initial velocity for this, which is 5/3 v0 cosine theta, t plus 0. I left off the plus 0 on this. This cleans up a little bit. Hey, here's x1. So how about I plug that in here? I've got x2 minus the quantity of v0 cosine theta times t, technically t1, equals 5/3 v0 cosine theta, also t1 times t. Because remember, the time is the same for both motions. In this case, we're going to have to do one more thing that I haven't introduced yet, but we're almost there. I can add v0 cosine t over to the other side. They both have the same terms. This is just 5/3 plus 1. We end up with the following. x2 equals 5/3 plus 3/3 v0 cosine theta t. I'm doing this a little bit quickly to keep us moving, but Anyone taking the APC exam, hopefully you're pretty proficient with math because you're gonna need it. x2 equals 8/3 v0 cosine theta t. Now this is great. x2 equals, these are numbers, v0 is allowed, theta is allowed, but t is not. And here is where the last part comes in, that we can look at something that up to this point we've ignored, the y direction for either of the motions. If you're one of my students, a big thing that we learned in projectile motion was your air time is determined by what's happening in the y direction for most of our projectile motion problems. So in this case, there are a couple of different ways that you can do this, but I think doing the total time from here up back down to the bottom would probably be the easiest. There are a few things that I'm going to do very quickly, but you could fill in only looking at the motion in A or the motion in B. If I do the full thing, my delta y is equal to 0 because I go up and come back down. My final velocity, well, I'm going to come back to that in just a moment. My initial velocity is v0 sine theta. And I know by symmetry, the up and the down aren't really being affected, so I'm going to end up with negative v0 sine theta. My acceleration is going to be negative g, and my time is going to be equal to 2 times t1, or what I've been calling t. With this, there are a couple different, like this opens up, the nice thing about this is you could use all sorts of things. If I use the equation v final equals v initial plus at, I could do the following. Negative v0 sine theta equals positive v0 sine theta minus g times 2t. I'm doing the minus from the minus g. I can add 2gt over to the other side and add v0 sine theta. So this gives me 2 v0 sine theta. But the important thing is this, when 2's cancel out, I can divide g from both sides and I get t1. The time that it takes for one of my bits of motion is going to be v0 sine theta divided by g. Okay, so I wasn't done because I had t in my answer. I can now get rid of t. x2 is equal to 8/3 v0 cosine theta times my time, which is v0 sine theta divided by g. You can simplify this. I think you'll end up with 8 times v0 squared times cosine times sine divided by 3g. And so you can simplify this, but you don't have to. This should be the correct answer. Okay, brief rundown on what I think the actual points are, because this one's a mess. There might be faster ways of doing this if there's even more tricks that you can use with either symmetry, or if you can get this velocity off of the graph that you made in the first part. But I think your first point is coming from a multi-step derivation beginning with a physics equation, of course. So +1 for multi-step derivation with at least one physics step, beginning with a fundamental principle of physics. I don't know if finding the speed or the velocity of piece R after the explosion is one of them, but I'm willing to bet that you would have the key things that jump out to me. That's one point there. Another point would be for having expressions. I'm going to underline these two. For having expressions for your displacements, x1 and x2, that you could use to actually correlate them to try and solve for it. Unless I'm overlooking something, it may be very difficult to go directly for x2 because you have different values of your speeds here, and as a result, that may cause problems. There might be a simpler way that I'm overlooking, but this is the way that comes to mind, at least to me. So I think this would be your next point, is by having a connection between these two. And then finally, I think this is an important part of it no matter which approach you take, but having an expression for the air time +1 for air time. Working for an expression for how long the thing is in the air. Okay, and then finally, I would expect that, I don't know if you would need to have the correct answer or not for full credit, but you might. So I'm going to go ahead and claim that it's there, at least for now. Otherwise, there might be an additional spot where they put partial credit. Okay, moving forward. Part C, the horizontal component of a velocity vector is represented by by Vx. Figure 4 shows the horizontal component Vx comma cm, the velocity of the center of mass of the projectile is a function of time t during the interval from 0 to t is basically from launch to explosion, and then we have not graphed from explosion to when they hit the ground again. They want us to sketch 3 lines. Remember how I said it was going to be worth 3 points? Okay, you're probably going to have more or less getting each of these correct and having them sketch and label all of the lines or curves. Now, they're throwing you for a loop on this because you're not actually going to end up with any curves. We want piece Q, we want piece R, and we want the center of mass. The first thing, and this is something that I've emphasized with my students, we have the center of mass tracks what the entire system is doing. What it was doing beforehand is given to us here, and since it's only interacting with itself, we end up with it's got to be doing the same thing afterwards. So one of the things is to draw this in and mark it VXCM, or yeah, CM, center of mass somehow. Our center of mass needs to be doing the same thing that it was before. We also need, we saw from our derivation that we would end up with, and I think this is why they have this marked, negative VXCM. We have the same speed, but going backwards. This one is piece Q, the piece that goes backwards. And then finally, at 5/3, that's not quite twice, but it's similar, somewhere up here we would have VR, or mark it as R. I guess that should be VQ, VXQ. I think as long as you have it R, Q, and CM, we can tell which ones you've got. You should be in good shape. I think it is 1 point for the center of mass line being continued. So if you drew that in a different spot or doing something different, then no dice. It could be that one of the points is for having flat level lines for all of them, which they should have, because there's only a very quick acceleration here, but then they end up with no net force as they're falling back down in the x direction, so we should have flat lines on this. You would also have one for having this at negative, the original value, and then I think this one would probably be a value above VXCM, hopefully around 5/3, but I don't think that you have to get it specifically there to get the credit. That's what I think for the 3 points. So this one continuing, this one Q at negative the value, because they have that marked out, and then R being a flat level line at noticeably above CM, hopefully around 5/3, a little shy of 2. Okay, finally, part D. Consider a case in which the projectile is launched at the same angle, initial speed, and when the projectile breaks into pieces Q and R, Q falls straight down. So our big difference on this, visualizing this, is the original was boom time, and then we have one of the pieces fall back down and hit here, and then the other piece go off over here and hit here. The new one that we've got is the stuff goes up exactly as it did before, boom time here, and this one falls straight down, so it has 0 velocity afterwards. And now they're asking, this one goes flying out over here, and now they're asking, is this greater than this, equal, or the same? Okay, this one, there are multiple ways that you could go about this, but hopefully for my students, one of the first things that comes to mind is this. Because of the much hated but very useful squirrel jumping at the bird feeder question that I put on many of my exams, so you'll probably recognize this one no matter what year is doing this, we would have the following. During a collision, when the total momentum of the multi-object system is conserved, another way that you can look at that is the impulse on one is mirrored by the impulse on the other, so that you have a positive of one of them and a negative of the other, so they would add up to having no change on the total system. That's an important thing to keep track of, and the key to being able to answer this very quickly. This distance depends on how fast object R, I think, whichever one is to the right, how fast it is going. So if V in this section is greater, we saw that this one was V equals 5/3 of V naught cosine theta. For the given time, we would end up with some distance. If this value over here, our new V, if it is greater than 5/3, so if it's, I don't know, 6/3, then this would be x new would be greater than x2. Or if it's less than 5/3, then we would have the reverse of this. And if it was equal to 5/3, we would end up with the same outcome. So here's the thing, you have to ask yourself. We're given information about the other piece, the one that I've marked in red. On this one, it was moving forward, and then we hit it and knock it back the other way. And if there's one thing that I've tried to drill into all of my students by you all getting multiple questions wrong throughout our momentum unit, momentum is a vector. Just because the numbers appear to stay the same or stay mostly the same, the direction is very important. It's much harder to stop something and then throw it back the other way than it is to simply stop it. In this case, we end up with a much greater delta P here for my red object, because not only was it moving to the right, but we stopped it and then moved it back to the left instead. So this one is a big delta P. Well, that means that this has to be a big delta P in the opposite direction, and therefore we would end up with a large value. Over here, we are just stopping this one, basically. So we end up with a smaller. Well, smaller on this one also results in smaller on this one. And therefore, we would end up with a much lower velocity. In fact, I expect that v would be less than 5/3. The other thing that you could do, instead of applying this rationale to conceptually, semi-quantitatively come to your answer, you could go through and you could actually solve it. In this case, we started off with 4 mv naught, and we are now splitting that into, well, the second object has 0 plus 3mv nu. So we could then, well, this is just 0 because it falls straight down. This is in the x direction, and I can divide this over, and we end up with 4/3 v naught equals v nu. This is also a perfectly good way of describing it, but you're still going to end up with the same outcome. Okay, this is 4/3. The original one was 5/3. So in the first one, it was moving faster for a given time. It will then end up going farther. In the second one, it's moving slower. So our correct answer should be that x nu is less than x2 for the reasons that we've described. Briefly justify your answer either by referencing a feature of the representations you drew in part A or C, or by using conceptual reasoning beyond algebraic solutions. In this case, we could go back up to our graph, our bar charts from part A, and we'd say, we originally had -1 here, and that means that we would end up with +5 here. Well, this would then become 0, and this would just be 4, and therefore piece R is moving slower. And for the same amount of time in our derivation, we showed that it was that, or we kind of assumed that, but now we're referencing a previous part. In this case, there are 2 points on this. One, I think for selecting and having an attempt to reference a worthwhile portion of your answers to previous parts, that's point 1, whether it's correct or not. The second point is for selecting the correct one and having a correct interpretation of how it relates to your materials. Okay, I think that's the walkthrough on this one. Until next time.